Hello student, welcome to the web optics course. Today we have lecture number 45 and we will going to discuss the Fresnel's half period zone and few more aspects of that. So today we have lecture number 45. So we have already started the discussion of the Fresnel's half period zone. So let me do that once again as a reminder that suppose we have a wave front that is propagating. This is a wave front, plane wave front that is propagating, and this wave front can be divided according to the Fresnel's theory with few zones like this. Such that if I have a point here P, the distance between the nth zone and the central to central point, if I write this is R naught, it is R naught plus n lambda by 2. That is the basic structure. So what we are doing, that if I want to find out the intensity at this point P, instead of considering the entire wave front, we can divide this wave front into few zones, and these zones are situated or are located in such a way that if I join the nth zone to point P, and if I join the first zone, the central point to P, if it is R naught, is the R naught distance, that is the perpendicular distance from the plane wave front to the point P, the point of observation P, this is R naught, then it is R naught plus n into lambda by 2. So with this notation it is easy to show. So let me draw these zones once again. So that we discussed in the last class, but I am doing this once again. So suppose these are the circles, concentric circles forming the zones. And each circle should have some area. I am shading the alternating zones so that one can understand how this is formed. Alternating zones I am shading. This is the way the zones are formed here, and this is the distance P, and this is R naught. So it is easy to show that the area of each zone is almost same. So area, for example, of the mth zone is simply, so last day we calculated that the area of the mth zone is roughly pi into lambda into R naught. That is the area of the individual zone, and it is approximately same for all the cases, because this right hand side does not depend on m. We can also calculate the radius of this individual zones that we did not calculate precisely. So, today we will do that. So, let me draw that. So, suppose this is the tip, this is the init zone I am drawing, and this is the central point. So, according to this is the init zone, and this is point P, this is R naught, and if I join this line from here to here, so that value is say R naught plus n lambda by 2. So, that is the way we are defining. So, if I want to find out what is the what is the radius, that is the this point, what is the radius of the nth zone, then we can also calculate that with very easy steps, and that is we have a equation. So, suppose the radius here is R n. So, I have simply R n square plus R 0 square is equal to R 0 plus n lambda by 2 whole square of that, or R n square plus R naught square is R naught square plus n R naught lambda plus lambda square by 4 n square. Now, this R square is going to cancel out, and essentially what I get is R n square is nearly equal to n R naught lambda, or in other word R n, because R naught in general is very large compared to the wavelength lambda. So, that is why I can neglect this lambda square term, and essentially R n is equal to root over of n R naught lambda. That is an interesting result we have, that this is the way the radius are defined for the nth zone, and based on the result what I do is this. Before that, let me remind that what we had, and that was, if I want to find out the intensity, and we get a remarkable result here, that this is the wavefront that is containing, that is the propagating wavefront, the same figure that I had used. So, this is a propagating wavefront containing zones like this. My drawing is not with the accurate scale, obviously I am drawing this by hand, but you should understand the concept. And then what happened, that if I want to find out what is the intensity or the amplitude at this point P naught, at this point P, what we find that the total the disturbance that we get, the amplitude that we get due to the entire wavefront, that is A n, is simply equal to A1 divided by 2. That is the contribution of the entire wavefront is summed up at the point P, and we find that it is nothing but whatever the contribution we have for the first zone, that is this zone, divided by 2. That is a remarkable result. Now, what we can do is this. Suppose we have a wavefront that is coming, and we have a aperture here. This is the wavefront that is coming with this kind of zones. And it is moving, and we also have an aperture here. This is the system where we have an aperture. The light is passing through this aperture, and this is P, and suppose here to here this distance is as before r naught. So, now if I increase the radius of this aperture, what happened that the P point will be gradually illuminated, and it will be illuminated most when the aperture r will be equal to, because here we know that Rn is equal to root over of n lambda r naught. That is the result we just derived. So, when the aperture is equal to, when this aperture radius is exactly equal to root over of lambda r naught, that means I am only allowing the first zone to pass through this aperture, then we get a maxima here in the point P. So, we get a maxima. Now, interestingly, if I increase this aperture to such that this aperture is allowing not one zone, but two zones, then what happened, this aperture will have a value like 2 of lambda of r naught. That means I am increasing the aperture to lambda r 0 root over lambda r 0 to root over of 2 lambda r 0. Then here only one zone is allowed to pass through this aperture, but here in the next case 2 zones are allowed to pass through. And we know that when there are 2 zones that is passing through, even number of zones that is passing through, the contribution of the amplitude is such that they are cancelling each other. And if that is the case, here we will going to get a minima. That is a very interesting kind of result. That means if I increase the aperture, that in general suggests that there should be we should get more intensity at point P, but here it is not the case. and that is happening because of the entirely because of the wave nature of these things. So, we get a maxima at point P, and if I increase more, then we will going to get a minima. In the similar way, if I increase more, then we are going to get maxima and minima. So, in general, when R is odd number, that is 2n plus 1 multiplied, this is the aperture width, aperture radius we are talking about, circular aperture for example, lambda r naught, then we get maxima. And when r is even number, this integer is even number, that is 2n lambda r naught, then we have a minima here. Here n can goes to 0, 1, 2, etc. Here n can goes to 1, 2, 3, etc. So, this is the way we can see that even we increase the aperture, the value at some point does not increase, the intensity at that point does not increase, but it is decreasing and it is changing in an alternative way. We will show that how it is changing in fact. So, also another important thing is if I change the location point, the distance, then we will going to see a similar kind of change. So, for example, before that let me also make few notes. So, note. So, note 1 is that if I increase the aperture, I discuss this issue, another issue. If instead of suppose having an aperture, if I have a opaque region, then what happened? If a circular opaque is placed in such a way that it covers the first half period zone, I write in short HPZ, then the resultant intensity will be the resultant intensity will be A2 by 2, because that we already calculated earlier, that what should be the resultant intensity square. If everything is open, then what happened, we have a resultant intensity A1 by 2 whole square. Now what I am doing, this is the way the wavefront is moving. Let me show the figure, and we place the opaque object here. So this is the way the other rays are contributed and coming this to this point. So this is the intensity of these things is A1, amplitude for this it is A2, for this it is A3, and so on. So the resultant amplitude, if I cover this, then the intensity will be proportional to the next one, that is A2 divided by 2 square. Now if I cover another in such a way that 2 zones are now covered, then the intensity will be A3 by 3, A3 by 2 whole square, and so on. So it will be this and so on. So in the previous case, we show that we have a aperture, and in this case we have a opaque object that we are placing in front of the wavefront in such a way that it is covering the entire zone, entire first zone, and then the intensity I am calculating at this point P. And if I increase this point, we can see that this value will go to change accordingly. Also another thing I like to note, and that is note 2 say. So this is the wavefront that is coming here. And over here I have several points, say P1, P2. I am moving towards or away from this whatever the aperture we have. Suppose at a distance P on this axis, what happened, that the aperture transmit only the first half period zone. So at this point, if I come forward, then the value of R0 will change, and since the value of R0 will reduce, we have reconstruction of the zone, because the zone area and the zone radius both depends on this value R0. So if I move from this point to this point, this value will going to change. So if it is such that the distance is such that only the first half period zone of the wave is coming here at this point, so that should be the the value of IP at this point, the intensity, that will be proportional to A1 square. That will be proportional to A1 square. In a similar way, if I widen the aperture for the same value, if I come and we need to widen these things, but for wider aperture for a near point of P1 on the axis, in such a way that let the axis in the aperture it transmit only the first half period zone, the only the first two half period zone instead of one, then what happened, the intensity IP1 will be now proportional to A1 minus A2 square. So, that is for other point. If I move other point, I change other point, the zone will be constructed accordingly, because as I mentioned, the zone construction depends on what is the distance from this point. So, I am moving over these points, and accordingly this intensity will going to change, and you can see that this value is very close to 0. Again, if I move another point, so this is IP1, IP2 and IP3, that is proportional to A1 minus A2 plus A3, and this is again a high value, because A1, A2 will cancel out, and this is high value. So, the point is, if I move along P1, P2, P3, the intensity variation is also should come as a, it change as a periodic way. Sometimes it is less, sometimes it is large, and that is also an interesting aspects of the Fresnel's zone. So, if I plot this stuff, so two cases are there. One, if I increase this aperture and we keep fixed the detector here, which is capturing intensity, what we find that there will be a variation of the intensity, and this intensity variation is to some extent period. I am just drawing a very rough thing. So, it will be like intensity will go down and up and down and up and down and up, something like this. Over this, if the radius of the aperture r is changing, if r is increasing. The interesting fact is, this is the intensity at point P. The interesting point is this minimus, that means even though we are moving, we are increasing the aperture, the intensity is reducing. In the similar way, we get a similar kind of figure. If I just plot the how the intensity is changing, if I move my, if I change my r naught, that is if I change this distance, then also we supposed to get a variation something like this. So, how this variation, what is the functional form is of this variation, we will, it shows that like a sinusoidal kind of curve, but there is also something more to it. So, we are going to discuss this in the later part of the lecture, but the point is here also we have, if you go towards the aperture or go away from this aperture, we will going to get not only the maxima, but also the minima. These periodic variations are there. So, today I like to discuss these few aspects of the Fresnel's zones. I do not have much time to discuss further about a instrument called the zone construction, or a instrument through which we can prepare this. So, in the next class I will try to discuss about this zones construction and do the detailed calculation and show that how the relationship is there with distance and wavelength, and we will find a nice looking expression like we get in the case of lens, it acts like a lens where light can be confined to a particular point. So, with that note, I would like to conclude here. Thank you very much for your attention. See you in the next class.